Yeah, sodium. Sodium's valence electron is not so tightly held, and so chlorine can come along and take that, no problem, and oxidize sodium. Since sodium's electron is easily oxidized, does that electron have high ionization energy or low ionization energy? What do you say? Low ionization, so it's easy to take. But what if we had a chlorine instead? If we had a chlorine versus chlorine, and each chlorine, what do they want to do? Each chlorine wants to take an electron. And so this chlorine wants to take this electron, this chlorine wants to take that electron. Will either of them be successful? No, because yeah, they're going to be same strength. This is like a tug of war. And so what's going to result here is chlorine is going to win. And we'll get this structure, sodium plus like this, and chloride like this. This is what we call the Lewis structure for sodium chloride. I'm not going to draw the entire lattice. We're just going to draw one formula unit. And the bond is between the two ions here. And so this is the Lewis structure for sodium chloride. Structure. Now, when chlorine tries to attack chlorine, neither of them are going to be successful, but it's not a lose-lose situation. It turns out to be a win-win situation, because what's going to happen here is this. They're going to end up struggling for that same electron, which is going to result in a sharing of electrons. And so neither side wins, but they aren't going to lose. They're going to just end up sharing electrons here. By sharing electrons, we do a weird count. It's easy to see. This chlorine, does it have an octet of electrons? 8 valence electrons? Yeah, 2, 4, 6, 8. This sodium doesn't have any valence electrons because we're down to the neon core. When we look at this, does the chlorine have 8? Well, it depends on how you count those electrons. And so we're going to count these in a strange way. The way we're going to count the electrons is like this. We're going to double count the shared electrons. So if we look at this chlorine's happy with 8 electrons, 2, 4, 6, 8. But then you'd think this chlorine would be sad with 6 electrons. No, we're going to double count the shared ones. So it's going to be 2, 4, 6, 8. So both end up with 8, what we call valence electrons, or an octet. So we end up with the octet here. And so chlorine can get an octet in 2 ways. Chlorine can take the electrons that it's oxidized something, form the ion, chloride, or it could share electrons like this, get the octet. And then we have that filled shell configuration. So looking at this PowerPoint here, it says that a chemical bond between 2 or more atoms that share a pair of electrons is called a covalent bond. Okay, it's a permanent bond. Typically we can form molecules this way, like this, where sodium chloride wouldn't form a molecule. Sodium chloride would form a lattice. And we don't have to form molecules. We could also form covalent lattices. Not ionic lattices, but covalent. The difference between an ionic lattice, like sodium chloride, and a covalent lattice is the type of bond. In an ionic lattice, we put the ions together and just pack as many positives around the negatives and as many negatives around the positives. The shape of the ion and the size of the ions will have an impact on that structure. For a covalent lattice, it's just covalent bonds that hold it together. So a covalent lattice like diamond, covalent lattice. So it's not just molecular compounds, but also covalent lattices. Again, just a repeat, molecules are the smallest particle. So this would be an example here. Hydrogen. Hydrogen can gain 1 or lose 1. Here in this instance, they both want to gain 1, let's say. If they gain 1, it doesn't form an octet, it forms a duet. Hydrogen, to fill the second, it's not the second shell, it's the first shell. To fill the first shell, we only need 2 electrons. So we just want a duet. And so this hydrogen tries to take an electron, this hydrogen tries to take, and we end up sharing, we end up with this. This is another way of representing that shared pair line. This is what we call a bond. So that's typically what we have here. We wouldn't draw this as a pair like this, we draw it like this. pair of electrons being shared. However, these pairs of electrons are not being shared. These are called lone pairs here. This is called a bonding pair here. Lone pairs. This one's bonding pair. And so when I look at this chlorine, it has 3 lone pairs and 1 bonding pair. This chlorine also has 3 lone pairs and 1 bonding pair. The bonding pair is double counted. Over here, we don't draw a line. Never draw a line for an ionic bond. We only draw a line for covalent bonds. So that's hydrogen. There are no lone pairs on hydrogen because hydrogen only wants to duet the left second layer. You know, covalent molecular compounds typically don't conduct electricity as well as ionic. This is just showing pure water, molecular compound, covalent bond. Table sugar is also a molecular compound, covalent bond. But table salt is an ionic compound. And when we dissolve these in water, sugar is soluble in water. When we dissolve salt in water, it breaks up into the ions. You can see covalent. Covalent compounds that do not break up into the ions. So this is what it's showing. This is an electrical conductivity apparatus. These 2 rods sticking out here are electrodes. So in order for electricity to flow, we need electrons to transport, or alternatively, we could have ions transport the charge between the 2 metal bases here, the 2 electrodes. So there are no charged species here, but there are charged species here. The ions, sodium ions and chloride. So I'd like both. All right, let's dig deeper into the covalent bonds. And the covalent bonds, like earlier we're looking at, you know, these are 5 valence electrons. 2 of the 5 valence electrons belong to the s orbital. The remaining, not 5, 7 valence electrons, sorry. 2 of the 7 belong to s, the remaining product belongs to p. And so what's going to happen is one of those chlorine orbitals is not going to be filled. Now this is what a p orbital looks like. This would be a 3p orbital. And that 3p orbital will have 1 electron. There'll be 2 more 3p orbitals that are full that I'm not going to show. So this is chlorine, 1. And then we have a chlorine on another. And when we try to visualize what's happening with the covalent bond, this is what's happening. We get orbital overlap here. Orbital overlap. And so a covalent bond consists of orbital overlap, merging of 2 atomic orbitals and their associated electrons to create a covalent bond. When we think about orbital overlap, you know, what's going to happen is there's going to be, in the overlapping region, there's going to be a higher probability. The probability is given by these dots here. So if I got dots here, I got dots here, then I'm going to have like twice as many dots here because we got 2 orbitals overlapping just in this region here. And so I'm going to have more dots here in the overlap region than in the non-overlap region. The p orbitals look funny. The p orbitals are these dumbbell-shaped orbitals. So I'm only overlapping one side of the p orbitals here, like this. Well, it turns out that the nucleus is positively charged here. And the electron density is negatively charged. So in this concentrated region here, I'm going to have negative charge, and that's going to attract the positive charges, and that's what's going to hold the atoms together. So here we can see with hydrogen. What I'm drawing here is the 95% boundary. 95% boundary would be this circle around here. What they're showing is electron cloud. So this electron cloud represents like the bird, bird position. So here's a 1s orbital on 1 hydrogen with 1 electron. This is the nucleus. Here's the 1s orbital on another hydrogen atom, 1 electron. What we do is we bring them together. When we bring them together, the 2 orbitals overlap. When they overlap, the density of dots is going to increase, because we got these dots from here and these dots from here, so the dots are essentially like doubling. Right? We got twice as many dots. Well, that means that these nuclei are going to be more attractive to this, what we call the internuclear region. The internuclear region is going to have a more negative charge density than the region outside the internuclear region. So this is our covalent bond. And so both ionic bonds and covalent bonds are electrical in nature. The ionic bond, we have the positive being held with the negative. In a covalent bond, it's a little bit more tricky to describe. In a covalent bond, we have an overlapping region of higher or increased electron cloud density, which creates a more negatively charged region. In other words, orbital overlap creates a more negatively charged region between the nuclei, which holds the two nuclei together, which creates a bond. So both of these bonds are electrostatic in nature, and this is why electrical forces are the key chemistry here. So overlap. So the same thing with fluorine. You put two fluorines, it's going to be a tie. They're going to have to share. Each fluorine is the most powerful oxidizer, by the way. Each fluorine wants to oxidize the other fluorine, but they are not going to be successful. But they aren't going to go home losers. They're going to share. So what we're going to end up with is this. Well, we visualize this. This is going to be a bonding pair here. And that bonding pair, we've got orbitals overlapping, creating greater electron density in this region. Now, we're going to take a look at that electron density here in a moment. But we talked about the lone pair, we talked about the octet rule. We're going to talk about bond polarity next. Bond polarity. Bond polarity is how the tug of war results. So for example, if I take a look at sodium and chlorine, pretty big difference in the strength of these. Chlorine's powerful oxidizer, sodium is a good reducer, sodium can lose that electron quite easily. And we result in something like this. When we look at the electrons, these two electrons here are now on chlorine. So the electron cloud is what we call localized on chlorine, or electron cloud on chlorine pretty much entirely. If we have something that puts up more of a struggle, like hydrogen, hydrogen is a lot harder to oxidize than sodium. Sodium's easy to oxidize. Hydrogen is much more difficult to oxidize. In fact, if there's a tug of war, hydrogen doesn't completely let go. Sodium completely let go of growth. Hydrogen is going to hang on. If hydrogen hangs on, what happens is this. Those two electrons don't automatically swing to chlorine here. What results is, if we look at the electron cloud, there's a distortion here. That means that, distortion like this. And so hydrogen hangs on a little bit to the electrons, a little bit. But chlorine definitely is more powerful. But it wasn't enough to ionize hydrogen. And so what results is a covalent bond. But this covalent bond is a little different than the previous covalent bond, because in the previous covalent bond, we put chlorine against chlorine. And chlorine against chlorine is going to result in something that looks like this, as far as electron cloud density goes. Yeah, we got two electrons in here. Draw like this, or I could draw them vertically or horizontally. But in the case of chlorine versus chlorine, it's a tie, it's split, so it's going to look very symmetric. Whereas HCl looks asymmetric. Now, chlorine wants that electron. It wants to form chloride, but it's not going to quite get there. Instead, what it's going to form is this, chlorine with a delta minus. Delta means small change, but in this context it means partial. Delta means a partial negative charge, not a full negative charge, a partial negative charge. A partial negative charge because more of the negative cloud densities around chlorine, which is going to result in less electron cloud around hydrogen, which is going to give it a partial positive charge. Over here, the charges are zero, zero and zero charges. And so we have different ways of calling this. This is called a non-polar covalent bond. This is called a polar covalent bond. And this one's called an ionic bond. Ionic bonds are the most polar. Polar means like a dipole, or a dipole would have a north pole and a south pole. We have electric poles as well. Electric poles have a positive pole and a negative pole. And so the most polar would be the ionic bond because we have a negative pole, the chloride, and a positive pole, the sodium. And then a little less polar would be the polar covalent, which would have a partial negative and a partial positive. And the least polar would be the non-polar, which doesn't have any poles associated with it. So this is in terms of polarity here. And so increasing polarity. So what we're going to do is we're going to come up with a broad categorization scheme and throw things. So what we got to do is we got to rank things in terms. What we're going to try to do is visualize a tug of war. You have a tug of war between two opponents, sodium versus chlorine, hydrogen versus chlorine, chlorine versus chlorine. And so what we're going to do is we're going to assign ranks to their ability to pull electrons. This is the diagram. On the left, is that polar or non-polar? Non-polar. On the right, this is the most polar you can get. The most polar you can get is called ionic. And this is somewhere in between. This would be called polar covalent. So non-polar covalent, polar covalent, and ionic. And so we want to look at the strength. The strength in this tug of war is called electronegativity. Electronegativity is the ability to pull the electron cloud towards itself. Which atom, which element do you think has the strongest pull for electrons? Fluorine. Fluorine is the most powerful oxidizer, should have the strongest pull for electrons. This electronegativity is what we're going to use to rank these in terms of strength, and the scale varies from pretty much 0 to 4. But 0 is not the lowest. Actually, the lowest is 0.7. Francium is the weakest, and fluorine is the strongest. So if you have francium and fluorine, it's going to be ionic. There's no problem. Fluorine's going to win. But when does fluorine start to lose? Or when does fluorine have to start to share? You know, fluorine doesn't want to share, but when will it have to start to share? And so we start looking at the general patterns here. And so what we're going to do is we're going to look at the strength difference. This is going to be called delta En, change in electronegativity. So electronegativity, let me complete this. Electronegativity goes from 0.7 to 4.0. 4.0 for fluorine, 0.7 for francium. And so fluorine's going to be the strongest, francium's going to be the weakest. And so when we pair them up, we look, you know, like chlorine versus chlorine. Chlorine's pretty strong, but chlorine versus chlorine, the difference is 0, so it's going to have to result in a tie. So we're interested in delta En. So we look at the delta En. Delta En of 0 means it's nonpolar covalent. But there could be slight differences in electronegativity. Let's say, what's a slight difference in electronegativity? The slight difference might be something like this. Carbon and hydrogen. Carbon and hydrogen. Carbon is ranked at 2.6, hydrogen's at 2.2. So 2.6, 2.2, they're kind of close. We call it close. And so that results in a difference of 0.4. You know, a difference of 0.4 is minor. And so what we'll see is if the difference in electronegativity is anywhere from 0 to about 0.5, it's pretty much nonpolar. You know, the polarity is so small, we'll call it nonpolar covalent. Polarity difference, electronegativity difference is so small, it's pretty much not. Carbon's a little bit stronger, but not much. So it's pretty symmetric, but just slightly distorted towards carbon. If we have an electronegativity difference of 0.6 to, let's say, about 1.5, this is not set in stone, then we have something that's polar covalent. So oxygen's stronger than hydrogen. Oxygen is 3.4. This is a typo, by the way. Hydrogen's at 2.2. 3.4, 2.2, the difference is 1.2. 1.2 is not enough. Oxygen will be incapable of stripping the electron. So that's going to result in polar covalent. But if we take something like zinc, you know, zinc chloride should be ionic. Let's take a look at zinc. Zinc is a 1.7, chlorine's a 3.2. So 3.2 minus 1.7 gives us a difference of 1.5. Zinc chloride's ionic, that's about a 1.5, so this is about, you know, 1.6 on. You know, right at the border, zinc chloride's 1.5, so it should be ionic, so maybe I should change it. Maybe I should, but then there are other examples where it falls on the other side. This is not a law, you know, this is just general observations. It's ionic. So electronegativity, if the strength is big, then it's going to be winner, take all. If there's no difference in strength, or very little difference in strength, then it's going to be even sharing. If there's a slight difference or a moderate difference in strength, then we're going to have uneven sharing. Polar covalent is uneven sharing. Now, when we look at these, we don't necessarily have to memorize these numbers, and we don't always need the chart, because what we need to know is where is the peak? The peak is here at fluorine, and then it goes downhill to francium. And so what happens with electronegativity is electronegativity increases as you go to the right and up. That's all we need to know. Therefore, sometimes we'll need the numbers. Therefore, we can tell, you know, what's more electronegative, carbon or oxygen? Well, oxygen is. Oxygen is closer to the peak, oxygen is closer to the fluorine. Now, hydrogen's funny, because look where hydrogen is. Hydrogen's in its usual spot. Where's hydrogen's usual spot? Above lithium. But that's not where it belongs in terms of electronegativity. In terms of electronegativity, hydrogen is between boron and carbon. You got to keep that in mind. Hydrogen is out of place here. It's between boron and carbon. Otherwise, everybody else is in place. Pretty much. There are going to be humps. You see those humps and blips? We're not going to worry about those right now. All right, then we have these examples here forming. We'll go back to the molecules. Here we have hydrogen and oxygen. Oxygen wants a total of 2, but in this case, it's got to take, hydrogen only has 1, so it's going to take 1 from each, so we'll need to bond 2 of those there. Let me just finish off with this. Here. Sometimes we'll form multiple bonds like this. These are 2 bonds here, because oxygen's got to form 2 bonds. Leave that unchecked. But there are other ways we could do it. We can form what's called a double bond. So if I have an oxygen here, oxygen has how many valence? 6. And another oxygen here with 6 valence. So each oxygen wants 2. So this oxygen is going to try to strip 2 electrons off the other oxygen here. And the same thing, likewise, this oxygen will try to strip 2 electrons off this. And so each oxygen is trying to strip 2 electrons, not just 1, because it's 2 electrons short. What we're going to end up with is this. We're going to end up with oxygen sharing altogether 4 electrons. And this is going to be written like this. Okay, and then nitrogen. Nitrogen has 5 valence electrons. So if we take 2 nitrogens, each nitrogen tries to gain 3. What we end up with is 6 electrons being shared. This. Or a triple bond. And so 3 lines represents 3 shared pairs of electrons. So that's the oxygen double bond, and nitrogen triple bond. It doesn't have to form double bonds and triple bonds to complete the octet. We can form multiple bonds the other way, like this. So for example, this nitrogen completes his octet by reacting with 3 hydrogens to complete the octet there. Okay, we'll stop here and then we'll continue this next